This is David Spears, Civil Engineering Instructor at Texas Tech University, talking about CE 2301 statics. Today I'm going to demonstrate how to do moment of inertia by double integration instead of using that trick and using a strip of dA being a vertical or a horizontal strip. And so this is going to be, I'm going to do this one on a shape over here that's got a y-axis boundary, and it goes along the y-axis from 1 to 4. The other method, we would typically use a horizontal strip for dA and integrate it that way. It's just another way of doing it. So I'm looking at the expression of that curve on the right is y is equal to x squared divided by 3. So I just rearrange that and I can say that x is equal to 3y to the 1/2 power, or the square root of 3 times y to the 1/2 power. For the differential element, I'm going to use dA is this red square, dimensions dx by dy, and I show x tilde and y tilde there in blue to that little differential element. Now the purpose of this, as I said, is to find Ix and Iy. So let's do Ix first. Well, Ix is equal to, by the second moment of area function, the integral over the area of y squared dA. We've been calling that y tilde. And because we're going to do a y-axis boundary shape, we want to consider first the inside the integral part first, and we want to consider of the x-axis, and then the y-axis is what we want to have on the outside. So we're going to say this is equal to the integral of, with respect to y, integral with respect to x on the inside, y squared dx dy. That's because dA is that value right there, dx dy. So we're separating the integrals out. So it's important that we use, because we're using a y-axis boundary, that we do this integral first, the part inside is with respect to dx. So we're going to integrate the inside integral first, which is real easy because it's just the integral of y squared dx is just, in this case, with respect to x, y squared is just a constant, so that integrates and evaluates to be y squared x. Now we can plug that value into the outside integral, the dy integral, and we can say that Ix equals the integral with respect to y of what we just figured out for the inside part, y squared x dy. Now we're evaluating the outside part of that integral. And in this case, we're going along the y-axis, so we want to go from 1 to 4. And so that evaluates to be y squared, and we just figured out what x is. We evaluated it here as the square root of 3 times y to the 1/2 power. So we put that in here. For x, substitute that in. We can simplify that and rearrange it, take that constant out, and we get the square root of 3 times the integral from 1 to 4. Y squared times y to the 1/2 is y to the 2.5 power, or 2.5 power, dy. So that evaluates to be square root of 3 over 3.5, y to the 3.5 power, evaluated from 1 to 4. At 1, that evaluates to be 0.4949. And at 4, it evaluates to be 63.35 approximately. And so we simplify that down, and that equals, we subtract one from the other, and we get 62.85. These are all inches, I forgot to say at the beginning. Inches to the 4th. So that's the answer for Ix. Now we need Iy, and we can repeat that process, except for the equation for Iy slightly different. It's equal to the integral over the area of x squared dA. So once again, we're going to keep the y on the outside and the x on the inside, and we're going to say that that's equal to that same to this integral now. Integral with respect to y, integral with respect to x, x squared dx dy. Looks very similar to that other one, except we have an x squared in there, and it's really the way we've been looking at it, calling it x tilde. And so once again, now we evaluate the inside integral, and we evaluate that as the integral of x with respect to x of x squared dx is equal to 1/3 x cubed. Now we plug that into the outer integral, and we're going to get that Iy is equal to the integral with respect to y of that inside part that we just integrated, 1/3 x cubed dy. Well, now once again we want to plug in the value that we have up here for x equals square root of 3 times y to the 1/2 power. So that's the integral from 1 to 4 of 1/3 times the square root of 3 y to the 1/2 power, and we have to cube the whole thing, dy. So we can evaluate that as square root of 3 cubed is, and divided by 3 is, works out to be 1.732, which is the square root of 3, or it's 3 to the, it's 1.732, and we're going to evaluate what it works out to be is, sorry, let me go back and erase that. Works out to be 3 to the 1.5 power, it's hard to say, divided by 3 times the integral of y to the 1.5 power, 1.5 power. Not very smooth, am I? Which evaluates to 1.732 over 2.5 y to the 2.5 power. It's easy for me to say. Evaluated from 1 to 4. At 1 it evaluates at 0.6928. At 4 it evaluates to 22.17. Therefore the difference between those two is 21.48 inches to the 4th. I always want to look at things and see which one I expect to be bigger. I see more spread, which is what moment of inertia is, about the x-axis, because I have this whole thing. See, I think this thing works out to be like the x value at y equals 4 is like 3.46, which I should always figure first. Anyway, the thing is obviously quite a bit more spread away from the x-axis than it is from the y-axis, so I'd expect that number to be bigger.